Okay, we're going to look at the scalar equation of a line. And recall that the standard form of a scalar equation of a line is ax plus by plus c is equal to 0. And we can develop scalar equations of a line from the vector or parametric forms. So last lesson we are looking at vector forms, and this lesson we're looking at going from vector form back to a scalar form. Okay, so recall that a vector form is really just this right here, OP is equal to, so the origin, sorry, excuse me, the position vector to a known point on the line plus t times the direction vector. And you can see that we have that right there. Okay, so x is equal to, we'll get the parametric forms, 2 minus 3t, so 2 minus 3t, and the y values for any point on the line is -1 plus 4t. Okay, and so those are my parametric equations. So what I'll do is I'm going to rearrange. Okay, and so I'm going to rearrange them and isolate for t. Okay, so if they're both equal to t, then I can equate them. So I can say x minus 2 over 3 is equal to y plus 1 over 4. And now that I have this right here, I can take both sides and I'm going to clear the fraction by multiplying by 4 and by -3. So 4 and by -3. So that allows me to cancel here, allows me to cancel here. Okay. So 4 is x minus 2, or 4 times x minus 2, and then -3 y plus 1. Okay, I'm going to expand that, and so I'll get 4x, and then I'm going to bring this -3y over to the other side, so plus 3y, and then 4 times -2 is -8. -3 times 1 is -3, but if I bring that to the other side, it's positive 3, and so we get 0 right there. Okay, so then I could say 4x plus 3y minus 5 is equal to 0. And as you can see now, I've got it in my standard form. Ax plus by plus c is equal to 0. So that's my standard form right there. So we put a box around it. Okay, the scalar equation of a line can also be developed using vectors if we know a point on the line and a normal vector, which is a vector that's perpendicular to the line. So, for example, a line contains p naught 7, 2 and is perpendicular to n, which is the normal vector 3, comma, -4. So let p xy represent any other point on the line. So what I'll do right here is I'll actually draw a line for you. So let's put in a line right here, okay, just so you can visualize this. Okay, and as you can see on the line, we've got a given point, and this given point right there is 7, 2, and that we have another point on the line that is just basically a generic point x, y, any other point on the line. We also have the normal vector, so the vector that is normal to this line right here, okay, and I'm going to color that one red, okay, and that's my normal vector, okay, and it's perpendicular, and it's given as 3, comma, -4. Okay, so what I'll do is I'll create a vector that goes from p naught to p. So I'll do p naught p is equal to, well, if I do the vector from p naught to b, it's the position vector from OP minus the position vector from OP naught. So I would just say x minus 7, comma, and then y minus 2. So that's my vector that goes along here, okay, from p naught to p. And then I also have my normal vector, which was given in the question as 3, comma, -4. Well, if I know that this direction vector here and this normal vector here are perpendicular, so I can say, therefore, p naught p dot n is equal to 0. So x minus 7 comma y minus 2 dot the normal vector, which is 3, negative 4, is equal to 0. So therefore, 3x minus 7 plus negative 4 y minus 2 is equal to 0. I'm going to expand that out. 3x minus 21 minus 4y plus 8 is equal to 0. And then cleaning this up, I get 3x minus 4y minus 13 is equal to 0. And that is the scalar equation of the line. Okay, putting a box around it, and we move on. Now, we'll derive this in a general form. A line contains p naught, x naught, y naught, and is perpendicular to n, which is given as AB. Let p, x, y represent any other point on the line. Well, literally, it's like the same thing, except now we're just using general points. So p naught p, well, p is x minus x naught, y minus y naught. I know my normal vector is given as a comma b, and the normal vector is perpendicular to this directional vector right there. So I'll say p naught p dot n is equal to 0. So x minus x naught, y minus y naught dot a b is equal to 0. And so now I'll have a x minus x naught plus b y minus y naught is equal to 0. Expanding this out, I get ax plus by minus ax naught minus by naught is equal to 0. And what you can probably see is that, remember, my scalar equation of the line is ax plus by plus c. So this whole part right there is just c. Okay, so the x and y coefficients in a scalar equation are the components of the normal vectors. So yeah, so like a and b were just the components of the normal vector. And the scalar equation of a line is given as ax plus by minus a x naught minus by naught is equal to 0, and we recall that that is just our constant. We just relabel that as the constant c, and we have to remember that a and b are the components of the normal vector, the vector that is perpendicular to the line. We're moving on. Let's use the above concept to arrive quickly at the scalar equation of a line. So this is a point on the line, and this is the normal vector right here. So what we'll do is we're going to write the scalar equation and then sub in the point to find c. We're not going to memorize the formula for c. Well, let's look right here. I have my normal vector 3, negative 4, so that's going to be my a and b. So I will say, therefore, 3x plus negative 4y plus c is equal to 0, or 3x minus 4y plus c is equal to 0. And I have a point, so I just sub that in. Sub 7 comma 2. So 3 times 7 minus 4 times 2 plus c is equal to 0. Isolating for c, I get negative 13. And so that's my scalar equation of a line. So therefore, 3x minus 4y minus 13 is equal to 0, and we'll put a box around it. Note that in these scalar equations of the lines, the coefficient in front of x is, by convention, a positive number. Okay, so if ax plus by plus c is the scalar equation of the line, then the NAB is its perpendicular vector, or its normal vector. And since the normal vector is at a right angle with the directional vector, then the directional vector has to be given as negative b comma a, or b comma negative a, because this dot product right here has to equal to 0. So AB dot negative B comma A has to equal to 0, or AB dot B comma negative A has to equal to 0 because the normal vector is perpendicular to the directional vector. And I'll go back to this diagram to show you that, right? The normal vector is perpendicular to the directional vector connecting points on the line. Okay, so it says find the normal to this line right here. Okay, this one's pretty straightforward. I'm just going to rearrange this. 2x plus y minus 5 is equal to 0. Recall that this is ax plus by plus c is equal to 0. And recall that the components of the normal vector are just a and b. So therefore, the normal vector is given as 2 and 1. Okay. Over here, instead of giving me a scalar equation line, they gave me a vector equation line, but they did give me the directional vector. And the directional vector here is 2, 5. But we defined it, or over here, that the directional vector has to have the components negative BA, right, because it is perpendicular to the normal vector of the line. Therefore, the normal vector is given as a comma b. Okay, so my a value is 5, and if my negative b value is 2, then my b value is negative 2. So alternatively, we can see right here that the direction vector is b comma negative a, right? So then the normal vector could also be, if it was pointing in the other direction, it could be negative 5 and 2, because this dot product here has to still equal to 0. Okay, state a normal of the line that is perpendicular to this line right here. Okay, so I'm going to say line 1 is given as 3x minus 4y minus 5 is equal to 0. So the normal for that line, I just look at the a and b values, is given as 3, negative 4, right? Okay, so and that's given, we've said that before, that's a, b. Okay. Now, if the normal vector of this line is perpendicular to the normal vector of some other line, n2, right, then that means that this has to have a dot product with this normal that equals to 0. So as we saw, that was the case over here. We can just say if n is equal to a, b, then and it's perpendicular with another vector, then we just say negative BA or B negative A. Okay, so if that's the case, then right here, therefore, N2 is equal to negative B comma A or B negative A. So then N2 is equal to, so I look at my B value here. My B value here is negative 4, so negative negative 4 is just 4. Okay, my A value here is 3, so that works right here. Or my B value, which was negative 4, and the negative A value, which is negative 3, this works right here. Okay. So again, right here, I'm given this as my equation of the line. I have 3x minus 4y minus 5 is equal to 0. My normal vector, as we saw, is 3 comma negative 4. But if line 1 is parallel to line 2, then the normal of 1 must be equal to the normal of the second one. And what I'll do is I'll show you that in a diagram right here. So I'm going to draw 2 lines. Okay, so 2 lines. Okay. And I'm going to make them parallel. And you can see that if I have the normal of one of the lines, the normal of one of the lines can easily be the normal of the second line, right? So if lines are parallel, they share the same normal, okay? So I already have the normal of this line, so therefore the normal of the second line is the same. Okay, find the scalar equation of the line which passes through 4, -5 and is parallel to this right here. Okay, so I'm going to say this is my line 1. It's 2x minus 7y plus 8 is equal to 0. So my normal for this is 2, -7. And I said already if L1 is parallel to L2, then N1 is equal to N2. So N2, the normal for line 2, is equal to 2, -7. So what I can do right there is I can say, well, therefore then, line 2 is equal to 2x minus 7y plus c is equal to 0, and then I'll sub the point that's given for -5. So 2 times 4 minus 7 times -5 plus c is equal to 0. And then I'll get 8 plus 35 plus c is equal to 0, and c is equal to -43. So I can say, therefore, 2x minus 7y minus 43 is equal to 0 is the equation of line 2.
In this example, we're going to find the scalar equation of the line that is perpendicular to this line right here, OP. And as you can see, OP is given in vector form. And so we're finding the line that's perpendicular to this line in vector form right here. And it also has passes through this point right here. So I've got a point on the line, and I know that it's got to be perpendicular to this. Okay, so I'm going to just put up a drawing here, and hopefully we can get a sense of how we're going to do this question. Okay, so in this drawing right here, you can see that I have line 1 and its direction vector right there. So that's what I'm starting off with right here, and I just kind of drew it arbitrarily, not really taking into account the the accuracy of it, right? So line 1 is this line right here, and this is the direction vector for line 1, right? So the direction vector for line 1 is -3, 2. Recall, we're trying to find the scalar equation of the line that's perpendicular to line 1. And so what do you notice about the normal of line 2 and the direction vector of line 1? Well, we can say, therefore, the direction vector of line 1 is equal to the normal vector of line 2. So I'll find or I'll rewrite the normal vector of line 2 is just equal to -3, 2. Okay? Right? And we can write a little statement here. We can say if line 1 is perpendicular to line 2, then the direction vector of line 1 is equal to the normal vector of line 2. So I have my A and my B, which I will use for the scalar form of line 2. So line 2 is equal to -3x plus 2y plus c is equal to 0. Recall that line 2 is perpendicular to this, so I have that information, but line 2 also passes through 4, 5. So I'm going to sub in 4, 5. So sub 4, not 4, 5, 4, -5, but I think you knew what I meant. -3, 4 plus 2 times -5 plus c is equal to 0. So isolating for c, c is equal to 22. Okay, so you'll see that I have, therefore, -3x plus 2y plus 22 is equal to 0. Well, when we're in standard form, we typically have the coefficient of x being a positive number, so I'll take both sides and I'll multiply them by -1. And so I'll end up with 3x minus 2y minus 22 is equal to 0, and I'll put a box around that. Okay, let's move on. So we're going to draw, or we need to find the scalar equation of a line that's parallel to this line right here, and passes through the point 4, -5. So let's start with this direction vector right here. Okay, so this is my vector form of line 1. So for line 1, the direction vector is equal to -3, 2. And so if that's my direction vector, recall that the normal vector is perpendicular to that. So if the direction vector is this, then the normal vector is going to be 2, 3. Now if you're wondering where am I getting these numbers from, well, we can go back up here and we defined it right here, that if your normal is AB, the normal is defined as being perpendicular to the direction vector. So that means that the normal dot the direction vector must equal to 0. Okay, so let's continue on right here. Now, if two lines are parallel, they share the same normal. We saw that right here, that if you have parallel lines, the normal vector of one line is the same as the normal vector of the other line. They share the same normal. So, let's continue. If line 1 is parallel to line 2, then the normal of line 1 is equal to the normal of line 2. So I can say, therefore, the normal of line 2 is equal to 2, 3. And so, therefore, 2x plus 3y plus c is equal to 0. I'm going to sub for -5 because that's the given point. So 2, 4 plus 3, -5 plus c is equal to 0. C is equal to 7. Therefore, ensuring that my coefficient of x is positive, 2x plus 3y plus 7 is equal to 0, and I'll put a box around that. All right, it says, in this example right here, find all vectors v of magnitude 2, which are perpendicular to 3x minus 4y plus 9 is equal to 0. Okay, so I'll state the equation of the line because it's already given to me. So line 1 is given as 3x minus 4y plus 9 is equal to 0. And so I know that this is my a and that's my b, and those are the components of the normal vector. So therefore, normal vector 1 is 3, -4. I'm going to find the magnitude of this vector. That's going to be the square root of 3 squared plus -4 squared. And that's going to be the square root of 25. And that's going to be 5. Okay, so I have the vector which is perpendicular to this line. That's the normal vector. Okay, and this vector right here has a magnitude of 5. So what I can do is I can find the unit vector that is perpendicular to this line by finding n cap. And n cap is just 1 over the magnitude of n times n. So n cap is equal to 1 over 5 times n, and n is 3, -4. But what you should remember is that this right here is a unit vector which has a magnitude of 1. Well, I actually don't want a magnitude of 1. I want a magnitude of 2. So therefore, v is just going to be the unit vector times 2. So then 2 times 1 over 5, 3, -4. So that's equal to 2 over 5, 3, -4. Now, this is the normal vector in one direction. So what I mean by that is I'll draw out a line and I'll show you that I'm finding one of the normal vectors. So there we go. So this is the normal vector that I've just found, for example. V is equal to 2 n cap, right? And as you can see, it's perpendicular to line 1, all right? Well, you might also think, well, there's another perpendicular vector here, and it is like this. And in this case, this would simply be V is equal to negative 2 n cap, just in the opposite direction. Both of these vectors fit the criteria of the question. They both have magnitude of 2, and they're perpendicular to the line. So I could also say, or V is equal to negative 2 n cap. So my final answer is going to be, therefore, V is equal to plus or minus, and then negative 2 n cap was negative 2 times 1 over 5, 3, negative 4, so plus or minus 2 over 5, 3, comma, negative 4, and I'll put a box around that. And there's my final answer to that question. Okay, homework is listed there, and thanks for watching.